Okay, so welcome. These are two very simple announcements here. Now we have exercise class this week, and assignment 7 has been uploaded. Okay, so I understand everybody is busy, so I try to pace out a bit. Okay, so assignment 7, I put this date here. I would like to do this. You see, I already defer it by a week. And assignment 8, I'm willing to push it a little bit later. Okay, if we follow our usual timeline, it should be the deadline for assignment 8, the next one, would be on 29th. But I'm willing to push it for a few days and push it in the reading week. Okay, so you have a little bit more time to do it, to think about this, but not much later than that, because there will be assignment 8 should be about statistical mechanics. Okay, another thing is I noticed the number of participants drops here. It would be nice if you begin to you tell your friends that if you know he or she is attending taking this course but not here, please encourage them to come. Okay, and then importantly, I need to switch off my video. Okay, so last time now I received some quick comments saying that you are not comfortable with this Lagrange multiplier. This is not something I can spend a lot of time here. Okay, I just want to maybe encourage you to look up a textbook, or maybe go back to other courses and refer to those notes. Really, because otherwise we are repeating things that have been done before. So just very quickly, this kind of now you might not be comfortable because I have a lot of terms here. I'm dealing with a very large number of variables. So I have this dn here, this dnj's. These are huge number of them. This j sum to infinity, right? I have a lot of terms like this. Okay, so maybe I can very quickly tell you that you can look it up or think about a simpler problem. Now, a simpler problem, for example, can be something like this. Let's say you are given a land, a piece of land, a huge piece of land, but you are only allowed to take an area of 100 square meters. Let's say you are only allowed to have a rectangle of 100 square meter. Okay, so a typical question is, what is the minimum amount of fence you need to make this? Okay, this is an optimization problem, and you don't need Lagrange multiplier to do this. But to make sure we are not crazy, you can try to use Lagrange multiplier and try to do it this way. Okay, so for example, just if we do this fence and area problem. Okay, now this is something you are very familiar. So if you solve it correctly, you will have confidence. So what do we want? You are given a fixed area. Okay, so this is I set it to rectangle. Okay, so to make it easy. So I will have an area of x times y. Okay, I have this area, and this is fixed. So I have x, I have y. Okay, so this is a constraint. This is fixed. So I'm usually in statistical mechanics, we don't write this out, but now this is a fixed number. This is a constant, just like the total number of particles is a constant. I don't write it out, but the meaning is there. So when I take ds, I get 0. Okay, so this is a constraint. Now, how do I do the differential? This is very easy. I have x dy plus y dx. This has to be 0. Okay, this is a constraint. Okay, and what is the quantity I want to optimize. Quantity I want to optimize is the total length of the fence. So that would be L 2x plus y. Okay, at the moment, I cannot say anything about maximum or minimum because I only stop at the first differential. I have no higher derivative for testing whether this is maximum or minimum. Okay, but it's fine. For statistical mechanics, the meaning of this is clear. So here, the meaning is also clear because you know this problem from high school. Okay, and what do we do here? We want to optimize this. So we are looking for a stationary point, right? Think about this as a function L of two variables. So I want a stationary point. So this DL is also 0, but the meaning is very different. Okay, so I will have 2 dx plus 2 dy. This I have to set it to 0. I have to set it to 0. Okay, and the Lagrange multiplier comes in here. How do you do? You need to simultaneously satisfy this dl plus the multiplier times the constraint ds. This has to be 0. Okay, so you plug this in, you will have okay, now I would really let you do it yourself, and you know the answer. You will get x equals y. Okay, so you know for this problem, if I set this to be a constant, I can only stop here. X equals y. I know if I have a square, this is how I optimize the problem. But why do we sometimes have to plug this in? That's because we want to solve a particular problem, and this is probably how you learn Lagrange multiplier before. You want to solve a practical problem. But here, let me. Now you probably don't feel comfortable because of the fact that I set this to be a huge number, a huge constant that you don't remember is a constant, and that is why this is a problem. This is why I guess, okay? And when you solve this, you plug it into here, in the constraint equation, you get your x and y. Okay, now by inspection, you can already see this. Now this constraint equation also tell you dy and dx are not independent, but I can arrange my lambda, right, to get one equation. And then dx and dy are linked like this. Okay, just like my dn's are somehow linked. So if I have one constraint equation, I can get one of the dn, like so. If I have one constraint equation, I can write one equation for dn1. And then you realize from the argument last time, I will be able to arrange all of this prefactor before dn's to be 0. Okay, so this is a very similar thing. Okay, this is simple enough. Another thing you probably learn is now suppose I have a mountain somewhere. So I'm going to draw you the equidistance. So this is the equidistance. So I have some mountain. Okay, and I arrange my coordinate system such that the peak of the mountain, so this is going up the mountain, the peak of the mountain is here, and I'm going to call this 0, 0. This is x, this is y. Okay, this is again a function of two variables. Right? If I know the explicit form, I will be able to draw this line for you. And the question I can ask is, what is the peak of this mountain? The peak of this mountain, you just do an optimization of f of xy. You don't have much to do. But why do we use Lagrange multiplier? The reason is sometimes you are not interested in the absolute, the global maximum. Suppose you now you build a cable car, and the cable car goes like this. Okay, cable car. You don't do a good job, and the cable car comes like this. This is your constraint. This line is your constraint. So you are optimizing this f of xy. subject to this constraint, because now the maximum is probably somewhere here. It's not the same as the global maximum. So this is when Lagrange multiplier plays a role. Okay, so it's not, I didn't do something completely new, but maybe you didn't recognize this relationship before. Okay, and you can find textbook with this kind of problem. It might not be a curve like this. It might be something very simple, a straight line. And then how do you write the constraint equation, and how do you solve the problem? If you find a few problems to solve, you gain some confidence. Okay, so now for the purpose of today's lecture, I need you to remember a few things. Wait a minute, is it this notes? Okay, so what have we done last time? Okay, so we look at distinguishable particles. So we look at, today we are going to continue this. So we look at distinguishable or localized particle. Localized particles. How do we describe them? We describe these particles to be in energy level E epsilon 1, epsilon 2, and this is a least epsilon Ka, and so on. And we are interested in how many particles are there in the energy level labeled by epsilon 1, and so on. Okay, so this is our picture. Okay, and we know the equilibrium, and this is the total number of microstates. When we arrive at the equilibrium, this will be a maximum value. Okay, and this actually comes from the fact that we can have different way to write this. Remember, I introduced this lowercase omega k. Okay, go back to the system with 3 particles. You will see how I list everything out. Go and the system of 6 particles. How do I list them? So these are related to this thermodynamic probability, which is the anomalized probability. Okay, if you add them up, you get the total number of microstates. But when you have a large system, very large system, we argue that this sum will be dominated by one particular type of configuration, and that will give you the equilibrium situation, equilibrium distribution, and that is what we were trying to solve last time before the midterm. Okay, so this has this interpretation from now on, and what you should think about is the following. If I have the total number of particles being n, how do I calculate this equilibrium distribution? I would look at this, I will count it like this. I have in total n particles, and how do I distribute them in this energy level? So I will have n1, n2, and nk, and so on. Okay, and what you should think about this is this will be the arrangement when you are at equilibrium. Okay, and therefore when we do this optimization, what we are after is a tiny deviation from the equilibrium distribution. What happens to d log omega? D log of big omega. Okay, so from here we have this log of omega. We will have log of n factorial minus the sum of this. I can write it as a product. So I have log of nj factorial. Okay, so I take this d log of omega. I have done this already, so I won't do it again. I will get this answer. Log of nj dnj. Okay, now I don't know how much you can remember. I will need this again, at least twice today. So I will tell you again, this is a box in green color. If you want to follow my presentation more easily, you can take a small piece of paper, write this down, and stick it in front of your screen, but don't block my writing, and that will help you. When this show up, you will know this comes from here. Okay, this is not a mystery. This comes from an honest treatment of this. You take the differential of that. Okay, so maybe just copy this down and stick it in front of on the wall or somewhere. Okay, and then we did this constraint, right? From here, we know we want to optimize this. So this is what we want to optimize. Okay, this thing has to be 0, right? We are looking for the stationary point. Okay, this has to be 0. And there are two other things that needs to be 0. So there is the total number of the particle is a constant. And the system is closed, so the total internal energy of the system has to be a constant. So this has to be 0, this dn has to be 0, du has to be 0. Those are the constraints, and this is what we want to optimize. So d log of omega has to be 0. So we use 2 Lagrange multipliers, set this to 0. Okay, and then we get here, we get this result. E to the minus alpha, e to the minus beta epsilon j. Okay, we reach as far as here. And today's task is to take this expression and try to get as many things as possible out from this. So this is one thing. Another thing, which is equally important, is we establish the statistical definition of entropy. Okay, this is the postulate 3 given in last chapter. So we need this today and this in the box. Okay. So what do we want to do? We want to discuss the meaning of alpha and beta. Now, alpha is kind of straightforward. Alpha, remember, this is very common in this part of the course. You might find discrepancy with the sign here. So some people don't put this minus, right? This is unknown multiplier anyway. So they choose to put plus, 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 then you have a minus sign here. Some would put plus alpha minus beta, but in any case, this symbol is almost always used to be associated with number, and this symbol associated with energy. Beta with energy, alpha with number. Okay, I'm going to stick to this. Okay, so alpha is number. What do we learn here? Okay, so let's write this again. By the end of today's lecture, you have seen this so many times that you'll be so sick of it. and me too. And therefore, this requires us to introduce the partition function. So we don't, that has a physics reason. Another good reason is you don't have to keep writing all this symbol. Okay, so this is what we get. Okay, so first, what is this alpha? Let's look at alpha. How do you get alpha? So you remember, if you do the summation, this n, j, you get big N, right? That's why when you do the differential, you get the sum of d little nj is 0. Okay, so let's plug it in. You just sum over j, you have this e to the minus alpha, and this is a constant, this is a multiplier, right? So this is really a constant. Okay, so we give it a very uninteresting symbol. This is A, we call this A. So if you know the meaning of A, you know the meaning of alpha. They are just related by taking the exponential. Okay, so now what did I do? I just plug in this expression, sum of nj. So this has to be big N. Okay, so I can pull this out, and that will give me n divided by A is sum over j. Okay, so if I know the meaning of beta, you can think of this as some kind of normalization for this equation to be true, right? Without this A, you have a problem. You have this thing summing to n. And this A serves the purpose of properly normalizing it, such that this expression is true. Okay, so there's a condition. We need to know what is the expression for beta. I actually told you that, but let's pretend that we don't know this. Otherwise, we cannot. You cannot enjoy this process of getting the meaning of beta. Okay. So let's extract the meaning of beta. This gives you another chance to use Lagrange multiplier. I'm going to look at this system here. I'm going to take my system, which I isolate from the universe. So this is my universe. And I'm going to put a rigid partition. So this wall is rigid. So this is rigid. Okay, so I will have N1 particle here and N2 particle here. And this particle cannot cross the partition. But I did not prevent the energy flow. Okay, so heat can flow, but particle cannot cross. Okay, so what we allowed? So the exchange of heat, exchange of heat is fine. Exchange of particle not allowed. Okay. So I'm going to make the notation consistent with my note. I'm going to call this the prime system. Okay, you will see why soon. So this is system 1, system 2, and system 2. I'm going to put a prime on some notation to differentiate between the two. Okay, so what do we have? We will have the sum of nj will be n1. So this is for system 1. And we can also write down the sum of epsilon j, nj. This will give me the total internal energy of the system 1. Okay? And for system 2, unfortunately, this j is used as summation index, so I cannot do too easily for you. So for system 2, I'm going to put a prime, and this will be n2. And likewise here, I will have this. So basically, I just look at this as 2 subsystems. Okay, so I set it up for you now. This is the prime system. Nothing new, really. Okay, now how do we do the constraint? The constraint will be this. I do not allow the exchange of particle, so my dn1 has to be 0. So this is a constraint. Okay, and dn2, similarly, dn2 is 0 because particle cannot leave, cannot be created here. So dn2 is 0. I say we can exchange heat. So in principle, the internal energy can change. Okay, so I cannot say du1 is 0. That would be too strong. But what I can say is because these 2 subsystems are enclosed from the rest of the universe, so what I can say is du1 plus u2 is 0. This is allowed. Okay, so I have 3 constraints, 1, 2, 3. So I need 3 multipliers. Okay, so if you plug this in, you get the corresponding differential. So this is nothing new. You just add the prime. So let's write this down. It's also nothing very profound. So let's write it. So for u1, you have epsilon sum over j, epsilon j, d and j. And for this, you have sum over j, epsilon j prime, d and j prime is 0. Okay, partition cannot move, so there's no dv, so there's no d epsilon term. Okay, what do we want to optimize? Same, we want to optimize this total number of microstates, which can be expressed in terms of the total number of microstates corresponding to system 1 and that of system 2. And last time we already discussed this. Right? When we discussed the entropy, I told you why we want to define it this way, because we want to add entropy. So I already partitioned the system for you to see the effect. We know if we have 2 subsystems, we have to write the joint total number of microstates like this. Okay, and again, this is nothing new. This is something you saw at the beginning of this lecture, as well as last lecture. Last lecture, I put in a lot of time for this. Okay, so this is system 1, and this is system 2. Okay, in the lecture note, the one I posted, I put in effort to color code things for you. So for the system 1, I use one color. For the system 2, I use another color. I try to be very careful to help you read my notes. Okay, and if you find typo, please let me know. I thought it's rather well polished, but still Harry managed to find typos. So, but still, I hope this improved the readability of the notes. Okay. Now I'm not gonna take the trouble to color code. That would be too much effort. But basically, you have two lines that runs parallel, and you just have to do it carefully. And I'm going to do it a bit differently. We already did it once. You get the same result, but I want to do it a bit differently. So for those of you who need it, you might appreciate this. Okay, so sorry, I don't want to write this equality. Now, what do I want? I want to optimize the log. So let me write the log first. The log of this. Okay, so I will have this log of n1 factorial minus sum over j log of nj factorial. Okay, and then I will have others related to n2. So I'm going to just put a bracket like this. Whenever you see this, this is associated with n2. You just add the prime. Okay, here you change it to 2. Okay, apply Stirling approximation. No, let's do it a bit differently. So I will before I ask you not to worry about this n1 because it's a constant anyway. When you do the differential, it will disappear. But today I want to do it a bit differently. Suppose you insist of using a Stirling approximation for big n1 too. Fine, it's no problem. Okay, I will have this minus the summation of this log. So this will be another Stirling approximation. Okay, minus nj. Okay. Okay, and you have the associated term in the square bracket for subsystem 2. Actually, I just want to show you this. So here you have this n1 log n1, which is of course constant. When you do the differential, it will still be gone. And then let's write this out. You have sum over j and j log nj. And then you have a minus here, you have a minus here. So this is a plus sum over j of nj. Okay, you have 1, 2, 3, 4 terms. Okay, use your chat and tell me which ones are the same. Term 1, 2, 3, 4. And type to me in private, please. Okay, 30 seconds. Just let me know. Huh? Okay, excellent. Now this is something people don't remember. Eventually they will forget. And this, they will just keep carrying this. But actually, if you sum over all this n, you get the total number. Okay, so if you sum over all this little n, you get the total number. So you have a nice cancellation here. Okay, so good. I get 5 correct answer. Okay, and then you have this. Now this is the only thing I want to show you. As I say, you can of course keep it this way. In the end, the answer will be the same. Just try to learn different ways to do things. Okay, now I take d log of omega. Okay, d log of omega, the first term will be gone. So I will only have one. The second and the fourth, these are cancellation. So I only have two terms left. Once I take the differential, because this is a constant, so I will have 0 for the first. I will carry this 0 for you. And minus the differential of this summation. Log nj. Okay, plus this whole thing here. Okay, the end result is you can do this yourself. I will just give you the result. This is sum over j, log of nj, dnj. Okay, for the first term. Okay, so d log will be this, minus log of nj prime, dnj. Okay, this is a little bit, sorry, prime. Okay, this is same expression or similar expression to the one I boxed in green color. So now you should look it up and convince yourself that this appear again. It will appear once more today. So I'm going to set this to 0. This is what I need to optimize. Okay, and what are the constraints? The constraint will be, I will have alpha 1 dn1. Okay, this has to be 0. Particle conservation, particle number conservation, and for the subsystem too. Okay, and for energy, du1 plus du2 has to be 0. Okay, I have 3 constraint equations, and this is what I need to set to 0. What's the next one? Sorry. Okay, so this is d log is 0. This has to be, these are the constraints. Okay, so next we set d log omega plus alpha dn1 plus alpha 2 dn2 plus beta du1 plus u2. This has to be set to 0. Okay, and if you plug in all this, I did this for you. This is in detail, and this, well, I don't want d of capital N. I want to express this in terms of d of lowercase n j that I can sum. No mystery here. This is identical to the case before, and if you do it, you get the result like this. So you have sum over j, right? So here you take the minus sign, so you have log of nj, and you have alpha 1, you have beta epsilon j. These are associated with dnj term. Okay, and you have this second term here, which involve the prime system. And again, you just copy and paste, really. So this is nj prime plus alpha 2 plus beta j epsilon j prime and dnj prime. Okay, so at this point, you just have to argue that these dnj's are independent from dnj prime. Okay, now we do not allow the exchange of particles, so really there's no reason why these two are linked. If the exchange of particle is allowed, I will have to deal with a term like this. So these two are really independent. Okay, so essentially I have two sets of equations to handle. So I have this, which is for subsystem 1, and this for subsystem 2. Okay, so dnj and dnj primes are independent, and then the rest just follow the argument we presented earlier for the single system, right? So if you look at here, there are only two multipliers, and if you look at this as a standalone system, you only have two, so you get the results as before. Okay, so same argument. Okay, the end results are at equilibrium. Remember, we are doing equilibrium distribution. So at equilibrium, I will have for system 1, again, I will get my exponential of alpha 1, exponential of minus beta epsilon j. This you can call it a1 if you like. It's okay, it's not important. Okay, the end result is for the subsystem 1, I have this way to distribute the particles. And for subsystem 2, I have this way to distribute the particles. Okay, and at equilibrium, there is one quantity which is shared among them, and that quantity is beta. Okay, now I put two systems side by side. I allow the exchange of energy and I reach equilibrium. And when I reach equilibrium, I can extract nj and nj prime. And then I look carefully and I realize, oh, these two distributions share one particular parameter, and that is beta. So beta is the same. Okay, and then I go back to my thermodynamics and I realize, oh, this is essentially what the zeroth law is telling us. If I put two systems in equilibrium, and when the equilibrium is established, there will be a common parameter, and that common parameter can be regarded as the temperature. Okay, and this is the common parameter, and therefore I can say that this can only be a function of temperature and nothing else. Okay, so this really allow us to move forward. Okay, so from the zeroth law, we know beta is only a function of temperature. That's not enough. I want something even more precise. Okay, so that will be what we should aim for after the break. Let's take a 7 minutes break, come back at 12:35. Okay, welcome back. What is this? Okay, so before the break, we have this result. So we are going to show, I want a more explicit form of beta. Okay, let's look at this. This is very fun. I really like it, and I hope you will like it too. Okay, Last time I wrote U. Okay, let's do this U again. The total internal energy. Now I already established that there's a beta here, so I don't need two systems anymore. I can go back to a single system and then try to see what happens to the system and see whether I can attach more meaning to beta. So I'm going to do just that. So the prime system already served the purpose of establishing that there's a common parameter, which we know is related to the temperature. Okay, that is the purpose of having two systems. And now we can go back to a single system and look at what happens with the internal energy. Okay, and this is simply given by Nj epsilon j. Okay, and this is really the accounting problem. You go and see how many particles are occupying the corresponding energy level. You do the product, write it down, and you move to the next energy level and see how many particles are there. And you add them up. This is your internal energy. Okay, so if you want to change the internal energy, there are two ways to do that. So now let's look at a more general case. One you have already seen is I would just move some particles from one energy level to the other. Okay, suppose I go and move a lot of particles from lower energy to very high energy. I increase the internal energy, right? So if I let's say I have 10,000 particles in N5, epsilon 5, I move half of them to epsilon 100, then I will increase the total internal energy. The other way is to do it like this. What I can do is I do not allow this particle to leave, but I change the energy level. I shift them. For example, I take all the energy level and add a constant offset of 1 eV. Then that will also change the internal energy. Okay, even though I keep the distribution the same. So these are the two ways to do it for this simple system. There's nothing much you can do. Okay, and then you begin to wonder what happens to these operations. Now you think in terms of thermodynamics. Thermodynamics, from the first law, you know this is TdS minus PdV. Okay, so for a simple system, suppose we still talk about PV system, this is the best you can do. And now you know how to look at the problem microscopically. Right? How do you get this change of the internal energy? One thing I can do is I take my system and squeeze it with pressure or change the volume. Okay, so if I change the volume, particle in the box problem tells me the energy level will change once I change the volume. Okay, so I can associate this term to this term. Okay, here, how do we analyze this? Actually, I already say that if somehow I have a way to change the occupation number, the description I gave might sound very crazy, but after all, this is related to heat flow, right? This is d bar q. How do I promote some particles from the ground state to the excited state? One thing I can do is to inject thermal energy. So if I give the system some thermal energy, if the particles can take advantage of this energy, they have to go somewhere. So they will go, the heat flow will allow them to enter the higher energy level, even though the energy spectrum remains the same. Okay, so we can identify this to be associated with this term. Okay, so this is the key link between thermodynamics and statistical mechanics. Okay, so I'm going to push forward and write TdS to be the same as this. Okay, so this is important bridge, but if you read all these textbooks, they always say one important statement. They always say there's one particular equation which is bridging the microscopic world to the thermodynamic macroscopic world. And that equation is our postulate 3. Okay, so if you take the postulate 3, if you stop here, there's nothing much you can do because you still have to learn how to deal with this ds. Okay, but it turns out that you know how to do that because this ds, we already established this, although it's a postulate, right? You need to start from somewhere. So most books list this as a postulate, and then you get, from here you get some result. Or the other way is you assume the Boltzmann distribution, assuming that you know beta. Then you work backward and you find the statistical entropy has to be given in this form. Okay, so I'm going to use the former, the way I presented earlier. So I'm going to plug this in and do the algebra. So from now, it's just algebra. Once you write this down, the rest is very manageable. Okay, so let's just do this. This is actually, I remember very satisfied when I look at this, when I first learned this part of the course. Okay, let me pull this KB out. This is Boltzmann constant. Let's just pull it out, and I write it more efficiently because I need space. Okay, and then this is a very typical calculation. It's something you must learn carefully. Okay, I'm not saying that the steps are trivial. In fact, if you are, if you see it the first time, you might not get it, get all the steps right away. But it's not difficult. Okay, so this is just very trivial. Write everything down. Okay, I don't want to waste more time now. Look up that piece of note I asked you to put in front of your screen. This is another time, another occasion that we can make progress if we know how to write this d log omega. So this d log omega is just minus sum over j. This is the one I boxed in green color. Log of n sub j dnj. Okay, and then the right hand side, I'm not gonna touch it now. Okay, and the next thing is, let me do you a favor. I'm going to, this is NJ, I just changed the color. This is NJ. Okay, so next, what do? I write KB, sorry. So I have KBT minus here. So I have sum over j, a log of this NJ we know. This NJ is the Boltzmann factor, right? This distribution. Sorry, the two colors are a bit different, but I think you forgive me. Okay. And this will help you revise. Okay, so I plug in the problem we have solved. This NJ is e to the minus alpha, I change it to a, times e to the minus beta times epsilon j. Okay, this whole thing should be in the summation sign. Okay, I will carefully put a bracket for you. Okay, then I have KBT, sum over J. Then I won't color code anymore. Okay, I will have log of, I will just expand this log A plus log of exponential and with a minus sign here. So I get a minus epsilon J for the second term. Okay, and this whole thing again is multiplied by D and J. So this J, this summation C is everything here. Okay. Okay, now use your chat again. Tell me which term is 0 inside the summation. Okay, the summation sign, see everything from here until the equality. There's a nice simplification. So use your chat and give me the answer in private. Okay, inside the summation, I have one term, two terms multiplied by D and J. Something is 0 here. Tell me which one is 0. Anyone? Okay, more? Okay, this is a guess or there's a good reason behind? Okay, I saw some answer, but it's not very confident, the answer. But why is it like this? Why is it 0? Why does it vanish? Okay, good. One nice answer. More? Okay, good. Okay, I'm happy. I get some good answer. So this term is 0. Here. This. Okay, cannot write. This one, of course, it's not 0, but this multiplied by sum over J, D and J is 0. Okay, and this is, I don't know, maybe it's obvious for you, but again, this is the kind of mistake I see a lot when I teach this part of the course. Okay, so, okay, I will write you what remains here. What you have here is you have a minus beta epsilon J, D and J left. Okay, now you have to, if you are here, it's worth remembering this, then you will face, you won't face too much trouble. We will have a lot of symbols like this to deal with. You might be lost later. And this is 0 because you sum over D and J, which is D capital N. And this is what we set to be one of the constraints, right? So D big N is 0. This is the constraint you should remember. Okay, so if you sum over J, D and J, this is Dn, so Dn is 0. Okay, but this is one thing. If you write it down like this, I'm happy. But then, strange enough, people begin to get a bit lost, and they will also write this to be 0. That would be a problem, right? So when you can only write this to be 0 when you sum over d and j, okay? And with nothing else in front, that requires you to do the sum, okay? All right, so this is a constant, you pull it out and sum over j, d and j, and you get a 0. And therefore you get beta. There's a minus sign here, there's a minus sign here, you get beta kbt. And then you have the same thing here. Okay, and that is written like this. And this is coming from the TDS term. Okay, and in the end, you get your beta as required. So this is another important result that you should remember. Okay, so think about all this logic here. We artificially allowed this discussion of having some heat flow into the system, and we artificially allow the volume to change. This allows us to discuss which term we can associate with the change of du. Okay, so from here we know we can associate the first term with the TDS term and the second term with the PDB term, and we focus on the first term, and that is what we have here. Okay, so the end result is you now know how to express beta in terms of temperature. And as I told you earlier before the break, or after the break, before the break, this beta is only a function of temperature. And this is why, this is how you see it. Okay, and finally, this is the full expression. This nj is something involving the normalization and an exponential of Eg divided by kBt. Okay, so this is very, very neat. We will get, this is the expression we are after. Okay. Now, a lot of maybe a lot of symbols here, but they are not too difficult. You just have to follow them, and this is really a very important exercise that you must do. Okay, let's move on with this. And you can see, at the beginning, I already told you, you get very tired of writing these exponential factors. So we can define something. So we can define, so this part is about partition function. Actually, let me write it as single particle partition function. Here it might not be very clear what is the difference between single particle partition function or otherwise, but I'm going to carry this symbol first and explain next time when I introduce another way to look at the system. So that will be the partition function for an assembly. You can also look at the system, you can enlarge the system size and look at an assembly and write a partition function for that. Okay, so this single particle will become clear when we compare with that scenario. Okay, so I'm going to define the partition function, usually it comes with this symbol Z. Because this is a German word, that means you sum over all states. Okay, so I'm going to put this notation for single particle, which I might drop later, but keep in mind that this is the definition of this partition function. Okay, this will just be this factor we see all the time. Okay, so this is our single particle partition function, which involve summing over all these exponential factors. So the symbol Z tells you really the action. You are summing over all these exponential factor, and each one has an associated energy level. Okay, and the English word partition then tells you a different way to look at the problem. That is to say, when you have the equilibrium distribution, how do you partition your energies? Okay, how many particles will take epsilon 1, how many will take epsilon 2? This information are encoded in the partition function. Another way to say that is, if you know the partition function, if you know this partition function for a particular system, you know everything about the system. You know all the thermodynamic information you want about this system. So in Blundell, he drew this cartoon. He drew a sausage machine. So if you input your partition function, you can output all kind of thermodynamic function of states. Okay, so let's see how to get this grand idea. This is really the big idea for this part. And therefore, it's important that you know how to write down the partition function. Now, if you only have two-level system, you might say, two-level, is it possible? Now, two-level system is indeed possible. If I only have two levels, I will only have epsilon 1 and epsilon 2. Then my single particle partition function will only have two terms. And with these two terms, I can have everything, I can calculate everything about the thermodynamics of this two-level system. And this two-level system is also similar to the coin problem we handle, right? The two-level there being head or tail. If I associate one of them to be of higher energy, one of them to be lower, then I can do, I can quantify it this way. Okay, so the key idea is knowing this, knows everything about the thermodynamic or the problem or of the system. Okay, first thing, what do we know? Suppose you want an expression for n, the total number of particles, which is a constant. And how do you express in terms of z? So this is quite simple. You know, you do this summation. Okay, and you sum over a times this exponential factor, and this a, if I want n sub j is a times exponential of this, right? So this a can be pulled out like that. So I will end up summing over the remaining. Okay, and this will be a times g. That's to say, if you know either n or a, you can find out the other. Suppose you know the energy spectrum. Okay. I will do it like this. This gives you another way to write nj. This is also commonly seen in textbook. It also is kind of Okay, I will write it first and explain to you. Now, this nj is summing over this. This is the expression for nj, right? Nj is a times this. Okay, so nj is a times exponential factor. Okay, nj is a times this factor. Okay, I don't want n, I don't want a anymore. I want to express it in terms of z. So I just change the subject, and this becomes n divided by z. Okay, and this is a common way to write it because it has a very nice interpretation, right? I can look at this as n times this exponential factor. Divided by the sum of exponential factor. I can look at it this way, right? So this tells me how to partition, how do I distribute these particles? These particles has to be some kind of weight, Okay, so how do I know? Now, I suppose this is n 100. How do I decide how many of this? What is the portion of n I should give to this epsilon 100? The answer is this. I will need to know what is the energy level for E100. Okay, you better tell me this in a way that, in a meaningful way that I can compare. So I compare, I'm doing thermodynamics, so I'm compared with the thermal energy here. Okay, and then divided by the sum of all these terms. Okay, and I will get the number which is proportional to this ratio. Okay, so this is a nice way to look at the problem. And I can keep going and on and on. Another way, here you should, it should also make you happy that this is some kind of normalization, right? Because this depends on this total number. Yeah, so in quantum mechanics, you do normalization by doing some kind of integral. Here we are dealing with discrete level, so we do this summation. Okay, so nj will be decided based on this kind of treatment. Okay, so this is simple, and the next thing will be messy. I'm going to do it my way. I think this is a good way to approach this problem. If you know a better way, write an email to me. So I'm going to investigate the derivative of z with respect to temperature and keeping everything else constant. Okay, all possible variables constant. I'm only interested in this derivative. Okay, so I'm not gonna explicitly write out the constants there being, the variables there are being held constant. Okay, you take this, sorry. Okay, I cannot erase. You take this expression and take the derivative with respect to temperature. Okay, so I'm going to do it. It's kind of messy, but not too bad. So first, I will have this exponential term untouched. Then I have to differentiate everything inside here. That will give me a minus sign epsilon j divided by kb. Okay, and then I have this 1 over t to deal with. So I will get 1 over t squared. Okay. Okay, let me tidy up. I will have kbt squared. kbt square outside, and this is minus two minus signs becomes plus 1, and then this I cannot pull it out. I have to leave it inside the summation because the summation sign will see this j and the original exponential factor, which is always there. Okay. Right, you know what I'm doing here. Okay, so this is one step. Okay, now I want to, I will leave it on the side. I need this result. So I'm going to label 1. Okay, another thing I can do is I want an expression for U, internal energy U. Why is this internal energy U? This is sum over J, epsilon J, and J. And now with everything we learn about beta, with partition function, we can write it down like this. Right, so E of J, we cannot do much. We'll just write E of J. Sorry, E sub J. N sub J, we know just a few lines above, we know N sub J is A times exponential of minus E sub J kBT. Okay, so A, this will be the full expression. Okay, but I don't like A anymore because I want to express it in terms of the partition function. And a few lines above, I'm going to drag slowly for you to see what is A. A is N divided by the partition function. Okay, so I'm going to, sorry, too much. So I'm going to do that. A is N divided by the partition function. Okay? This is simply the internal energy U. Didn't do much. Now, the only thing you might want to know is I have changed this A to this. You will figure out anyway, but this is the advantage of attending lecture. When you see the note, you don't need to work it out yourself. Okay, now this N is a constant. I can pull it out, but the rest, I cannot do much. My undo button doesn't work anymore. This is summing over J, epsilon J, epsilon sub J, e to the minus J kBT. Okay, so what do I do next? I have this N divided by Z that I cannot do much, but I look at this sum over J, epsilon sub J exponential. You see, I write it close to each other for you to compare. So you know this, everything in the summation sign can be related to this partial derivative from 1. Okay, so this is from 1 above. I can write this as partial derivative. Sorry. Okay, this term multiplied by this kb t squared. Okay, now this is a very famous result. So U can be written in a very compact form. This is n kbt square, and I have 1 over z, and I have partial derivative. I can move it in and make it into a log. Okay, this is so important that I will box it for you again. So once again, If I know how to write my partition function, I know how to write the internal energy right away. I just take the derivative. This is another function of this sausage machine. Okay, two more, then I will let you go. The next thing is entropy. Entropy, again, the aim is to write it in terms of Z to show you the argument. So first, how do you do this kind of thing? Once you have experience, you will know how to do it quickly. I want to express this in terms of epsilon sub j and sub j, so I have a chance to relate to the partition function and to build my argument. Okay, I will write you maybe the first line. This will be eventually it will be this n log n business minus summation of nj log nj. Okay, this is the same thing you have seen before. Okay, and this is an exercise you should do, and in the end you get this result. Okay, now this requires two steps to build the logic. If you know the partition function, you know the first step is to get the internal energy U. Okay, so this becomes known. Okay, n is a constant, it's a system parameter, and you know the partition function. So if you know the partition function, you know the entropy as well. Okay, this is brilliant, right? If you know the partition function, you know everything about all this. Okay, last, this is related to the assignment question a while ago. I already hinted to you that there's some kind of mysterious function z that you can that allows you to do this kind of treatment. And there I explicitly link it to Helmholtz and then Helmholtz function f. And now I want to provide that link. There I told you if you know z, you know how to calculate f. And because f has a natural variable of t and v, and from there you know everything about the thermodynamics. Okay, so I gave you that expression in the assignment, and now I want to derive that expression for you. Okay, so I look at this S, the expression for S, and I will start from this. I will multiply the expression for S by temperature T. Okay, so when I do that, I have kBT and then N log Z for the first term. For the second term, I will have, I multiply by T, right? So I have kBT cancel with this kBT, so I only have U. Okay, so now I change a little bit. I'm going to move this to the other side and TS to this side. So I will have U positive plus U minus TS. I move TS to this side. And this to the other side, I will have N kBT log. Okay. All right. Since you have just taken the midterm, so you realize this is just F. Okay. So if I know the partition function, I also know F. So I can keep going and on to get all the other parameters, following the our knowledge of thermodynamics. Okay, so that is it actually. Next time I want to next on Wednesday I want to still talk about this partition function. where miss? Oh, sorry. Thank you. Okay. So next time I want to talk about this partition function again, but I'm going to look at it a bit differently. And then and still, when we introduce gas, which is the situation when the particles are not distinguishable, we are going to look at the partition function again. So this is kind of important. So before you come for the Wednesday lecture, please spend some time to revise this. Okay, thank you very much. That's enough for today.